A Cambricon Accelerator die is on the table, pulled from a data center rack and photographed under oblique light, the package still bearing the faint residue of thermal interface material from the server it last cooled. This is the first product from a Chinese artificial intelligence chip company to report a full year of profitability, and its exterior gives almost nothing away. The marketing surface describes a chip that competes with the best data center accelerators in the world. The layers beneath that surface describe something more specific, more constrained, and more legible once the package is removed. What the dissection identifies at the bottom is not what the top suggests. The architectural decisions that make this chip distinctive are not purely strategic choices. They are the fingerprint of a manufacturing ceiling that was imposed from outside and that shaped the design from the transistor level upward. The cuts run in this order. The package comes off first, then the die's functional block map, then the compute array's internal logic, then the memory subsystem, then the point where this design deliberately parts from the Nvidia reference it is clearly reading, and finally the Foundry constraint that determines everything above it. The package separates in the usual way, heat and mechanical pressure releasing the lid from the substrate cleanly. Underneath it sits an accelerator die in a standard high-performance compute carrier, the thermal paste contact still faintly visible on the lid surface. The form factor places this chip in a data center server slot, alongside the power delivery infrastructure and memory modules that large model training and inference require. Before any circuit on the die is examined, the package has already stated something structural. Whoever designed this chip was designing for the same physical environment as the parts it is meant to replace domestically. The power envelope implied by the package dimensions, the server slot form factor, and the thermal regime visible on the contact surface all belong to the same class of operating conditions as the Nvidia H-series parts this accelerator is positioned against in domestic procurement conversations. The package is the most ordinary layer, and it is the last ordinary layer. The first cut inward is where the decisions become legible. The die's interior divides into recognizable zones. A large fraction of the surface area is occupied by a matrix processing array, which is Cambricon's terminology for the dense parallel compute block at the center of the design. Around it sit memory controllers, an interconnect fabric linking the compute block to the memory interface and supporting logic for scheduling and data movement. Cambricon's own technical publications are consistent on this overall organization, though die photography at the resolution needed to independently count individual processing elements and confirm precise block boundaries has not been published by any third party as of mid-2025. What follows at this layer draws on the company's published architectural documentation and on inference from the power and bandwidth specifications Cambricon has released publicly. This block map will look familiar to anyone who has examined Nvidia's data center accelerator dies. That familiarity is not coincidence, and the dissection identifies it as convergent rather than imitative, at least at this level of resolution. Training a large language model is, at its computational core, a sequence of very large matrix multiplications, weight tensors being applied to activation tensors, layer after layer, with gradients flowing back through the same structure during training. The chip that handles this workload most efficiently is the chip that devotes the largest share of its transistor budget to executing those multiplications in parallel, feeds the compute unit's data fast enough that they are not waiting on memory, and moves results out fast enough that the next operation begins without delay. That description fits the block map visible in Cambricon's documentation. It also fits every serious competitor in this market. Both Nvidia and Cambricon arrived at this shape by reading the same mathematical constraints. The shape is the answer the math demands. The block map proves that Cambricon is solving the correct problem. It does not yet prove how well, and the layers beneath it are where the genuine divergence begins to appear. The compute array is the layer where specialization becomes structural. Nvidia's data center accelerators carry the accumulated weight of a graphics heritage. Tensor cores, optimized for the matrix operations at the heart of large model compute, sit alongside execution units that handle the full range of shader operations a rendering pipeline requires. Those units exist because Nvidia's product must remain programmable across a decade of customer code written for CUDA, must run graphics workloads in the context where that is required, and must support research workloads that were not anticipated when the chip was designed. That programmability infrastructure costs transistor area. It is a cost Nvidia pays because its product history and its customer ecosystem require it. Cambricon does not have a graphics business. It does not have a CUDA compatibility obligation. Its compute array, as described in company documentation, is organized around the precision formats that transformer training and inference consume. The company emphasizes support for BF16 and INT8 precision, which are the formats that running and training large models at scale actually use. The chip does not carry the transistor overhead of general-purpose shader programmability. It does not need to. This is the first point at which the dissection identifies genuine divergence, and it is worth stating precisely what that divergence means before stating what it implies. It means the die allocates its transistor budget differently from a general-purpose GPU. It does not automatically mean the die performs better per unit area at any given task, because that depends on the process node the design was fabricated on, the memory bandwidth available to keep the compute units fed, and the efficiency of the interconnect fabric. Those layers come next. What the compute array exposes at this depth is a deliberate structural bet that the market this chip is targeting is narrow enough and stable enough in its workload requirements that general-purpose programmability is a cost Cambricon does not need to pay. Whether that bet is primarily a strategic choice or primarily a response to constraint is the question the deepest layer will settle. Cambricon's published peak performance figures for its flagship Accelerator series state throughput in tera operations per second across integer and floating point precision formats. The company states these figures are measured at chip level rather than extrapolated. No independent benchmark at scale has been published by a third party for the current generation as of mid-2025, so the dissection treats these as company claims pending external confirmation. The compute array that those figures describe is purpose-built in a way that a general-purpose GPU is not, and the transistor area freed by eliminating graphics programmability goes somewhere. The architectural documentation and the published performance claims together suggest it goes into more compute units within the same die footprint. Whether the resulting throughput reaches the claimed figures in a production environment against real model architectures at production batch sizes is one of the three things this dissection cannot settle, and that caveat is addressed directly later. The memory subsystem is the layer where a constraint imported from entirely outside the die becomes visible. A compute array that executes matrix multiplications at the rate this chip's specifications describe must be continuously supplied with the weight matrices and activation tensors those multiplications consume. If memory delivers data more slowly than the compute array can absorb it, the array idles, and performance falls toward the memory delivery rate rather than the compute peak. The ratio between compute throughput and memory bandwidth, a quantity engineers track as arithmetic intensity, determines how often that happens for a given workload. Large transformer models, particularly during inference on long sequences, can push into memory bandwidth bound regimes where the compute array's peak throughput is never reached because the memory interface cannot deliver data fast enough to sustain it. High bandwidth memory, stacked DRAM dies bonded directly to the accelerator package, is the industry's solution to this problem at the high end of the market. The stacking geometry places memory dies physically close to the compute die, shortening the electrical paths that data must travel, and delivering bandwidth that conventional DRAM attached to a printed circuit board cannot approach. Cambricon's published memory bandwidth figures, taken at face value, are in a range that analysts covering the Chinese semiconductor market have attributed to memory in the high bandwidth class, though the company has not publicly confirmed its memory supplier or the specific generation of memory technology in current products with the specificity that would allow independent verification. The analysis treats this as analyst inference, not established fact. What is established is that domestic Chinese production of high bandwidth memory at the density and bandwidth required for data center accelerators does not exist at scale as of mid-2025. The companies that manufacture this class of memory are not Chinese domestic suppliers. Whatever memory technology sits on this package arrived through a supply chain that crosses international borders regardless of where the compute die was designed or where it was fabricated. That supply chain dependency is invisible from the package exterior. The teardown exposes it as a structural fact about this object. The die inside is Chinese designed and Chinese fabricated, and it depends on a memory supply chain it does not control. That dependency is not unique to Cambricon among Chinese chip designers, but it is present in this specific object and shapes what the object can do at the memory bandwidth layer. The divergence from Nvidia's design scope is not primarily in the block map, and not even primarily in the compute array's precision focus. It is in the intended operating range of the finished chip, and it shows most clearly when this accelerator's target use case is examined alongside Nvidia's. The H100, the part Cambricon's accelerator is most frequently positioned against in domestic procurement narratives, is designed to serve a wide range of large compute workloads simultaneously. It trains frontier-scale models, runs inference on deployed models, supports research applications that use its programmability for tasks that were not defined when the chip was designed, and connects to other chips through a high-speed fabric for multi-chip training runs that span thousands of accelerators. It is a general instrument for large-scale computation. Cambricon's documentation emphasizes inference throughput and the specific precision formats that running already trained large models requires. Training at the frontier scale, the workload that demands the most advanced process node, the highest memory bandwidth, the most sophisticated multi-chip interconnect, and the largest raw transistor count is where this die's ceiling is most visible. The ceiling is not primarily architectural in the sense of a design decision that could be revised in the next chip generation. It is set by manufacturing, and understanding why requires going to the layer beneath all the ones examined so far. The relationship between process node and architectural scope works like this. A smaller transistor budget forces a designer to choose what to leave out, and those omissions define the design as clearly as what was included. Cambricon chose to leave out general-purpose programmability and the transistor overhead of graphics compatibility. The block map reflects those omissions, so does the inference focus. A chip designed to run already trained models rather than to train frontier models at scale can reach commercially useful throughput figures within a transistor budget that could not support a general-purpose competitor to Nvidia's current flagship. That is the link between the manufacturing ceiling and every architectural observation above it. SMIC, Semiconductor Manufacturing International Corporation, is China's most advanced domestic foundry. Its current leading-edge production capability, as of mid-2025, is widely reported across industry and financial press to be in the range that TSMC would classify as the 7-nanometer class, achieved through multiple exposure patterning on lithography equipment that predates EUV. TSMC's current production scale nodes are more advanced. ASML's extreme ultraviolet lithography systems are not available to Chinese foundries as a direct consequence of export controls that the United States, the Netherlands, and Japan have applied to advanced semiconductor manufacturing equipment. Cambricon is understood to use SMIC as its primary foundry partner for current generation products. This has been reported consistently in industry press, though Cambricon's public disclosures have not confirmed the specific node designation with the precision that would allow direct comparison to TSMC's node naming conventions. The node gap between SMIC's current production capability and TSMC's leading edge is a matter of established public reporting. Its exact magnitude depends on how nodes are defined and measured, but its existence is not in dispute. A chip fabricated on a less advanced node contains fewer transistors per unit of die area than a chip fabricated on a more advanced node at a given die size. That transistor density difference sets a ceiling on how large the compute array can be, how much on-chip memory the design can afford, how efficiently the interconnect fabric can be implemented, and how much total compute throughput the chip can deliver within a power envelope that a data center cooling system can manage. A chip on a less advanced node that achieves a given throughput typically dissipates more heat per operation than a chip on a more advanced node achieving the same throughput, because the older process is less power efficient at equivalent performance. At the scale of a data center rack filled with accelerators running continuously, that heat difference compounds into cooling costs, power infrastructure requirements, and physical density limits that do not appear anywhere in a single chip specification sheet. The way a chip designer responds to a smaller transistor budget is specialization. Concentrate every available transistor on the function the target workload actually requires, and eliminate the functions it does not. That is the architectural story this dissection has been tracing from the block map through the compute array and the memory subsystem to this point. The specialization is real. The inference focus is real. The departure from Nvidia's general purpose scope is a genuine and measurable characteristic of this design, but the dissection cannot separate how much of that specialization is a deliberate strategic bet on a market the company is confident will remain narrow and predictable, and how much is the only coherent architectural response available within the transistor budget that domestic foundry capacity provides. Both are true simultaneously, and the layers of this die do not distinguish between them. The manufacturing ceiling is not a footnote to the architecture. It is the condition under which the architecture was designed. The dissection has limits, and stating them plainly is part of the analysis rather than a qualification of it. Cambricon's performance figures are the company's own claims, and no independent large-scale benchmark covering the current generation has been published by a third party as of mid-2025. The throughput numbers in the specification sheet describe a chip running under conditions the company controls. What those numbers become in a heterogeneous production data center environment against real model architectures at production batch sizes with the memory and thermal constraints that a full rack imposes is not publicly established. The gap between peak specification and deployed performance is a standard condition across the industry and is not unique to this company, but it means this dissection cannot confirm the performance layer of its analysis from independent data. The die photography and internal block analysis that would allow a circuit-level examination of Cambricon's architecture has not been published at the resolution that equivalent examinations of Nvidia parts have achieved. The architectural conclusions here rest on company documentation, analyst inference, and structural reasoning from published specifications. High-resolution die photography at the level of individual functional blocks might confirm those conclusions or might revise them in ways the current evidence cannot anticipate. Until that data is available, the block map analysis is a reading of the accessible evidence rather than a confirmed physical measurement. The process node difference between SMIC's current capability and TSMC's leading edge affects not only transistor density but also power efficiency at a given performance level and the feasibility of the multi-chip interconnect fabrics that frontier training runs require. The teardown examined one die. At data center scale, racks of these accelerators running continuously. The system-level consequences of the manufacturing ceiling extend beyond the single die in a way that a single chip dissection cannot fully characterize. Taken together, these limits mean the dissection can confirm the architecture's overall shape and the manufacturing constraints' existence and structural influence with reasonable confidence, while leaving the precise magnitude of the performance gap and the system-level efficiency question as open items that independent data would need to resolve. What the whole object proves, read in sequence from package to foundry, is this. The restriction imposed to prevent access to the most advanced semiconductor manufacturing equipment did not prevent Cambricon from building a commercially successful accelerator. It determined what kind of accelerator Cambricon built. The 453% revenue growth the company reported for its most recent full fiscal year is real market data. The analysis identifies what it actually measures, not the chip's performance relative to Nvidia's H100, but the gap between domestic demand for inference compute and the accessible domestic supply of it. Those are different quantities, and conflating them would misread both the commercial success and the technical position. A chip that trails the global state-of-the-art by a measurable node distance can still produce that revenue growth simply by being available to buyers who cannot legally access the alternative. The demand is large, the accessible supply is small. The chip fills the gap that the export controls created. The specialization is the restriction's fingerprint. A company with access to TSMC's leading-edge nodes and the process margin that comes with them would not have made the same architectural bets. It would not have needed to narrow the design scope so precisely to what domestic inference workloads require. It would not have needed to eliminate the transistor overhead of general-purpose programmability quite so completely. Cambricon made those bets because the manufacturing ceiling made a general-purpose competitor to Nvidia's current flagship unachievable at comparable performance within domestic foundry capacity. So the design moved to the ground that was achievable, a narrower, inference-focused object that fits within the transistor budget that domestic fabrication provides, serves a domestic customer base that cannot legally access the global alternative, and generates revenue at a rate that the structural imbalance between demand and supply makes nearly automatic. The chip is profitable. It is also a record of a constraint. Both of those facts are legible in the same layers, and the dissection shows why they are not contradictory. The restriction did not stop this chip from existing. It decided what this chip is. In the comments, name the next object you want opened. The chip that renders graphics and trains large models on a single die is one candidate, and there are others. The one that draws the most specific requests is the one that goes on the table next. If this approach, one object taken apart cut by cut until the buried constraint becomes visible, is useful to you, subscribe and turn on notifications, because the next dissection is already being prepared.